Hi, it's me, Dr. Rahifa. In this video, I'm going to explain another example of Fourier series of half range. At the end of this lesson, students should be able to solve the Fourier series of half range. The question is, find the half range Fourier series for the function ft equals 1 minus t squared, t from 0 to 1. It's a half-range function where the function is given within the interval t from 0 to 1. Therefore, from the question, we know that L equals 1. We're going to find the half-range Fourier series for the function using A, even function expansion, and B, using odd function expansion. Here is the plot of the function using the even function expansion. Firstly, we need to sketch the half range ft equals to 1 minus t squared t from 0 to 1. In order to expand the function into an even function, we need to make sure that the plot is symmetry about the y-axis. And the next step, expand the function within the interval t from minus 3 to 3 with period t equals 2 by repeating the plot identically. Since it is an even function, therefore, we're going to use Fourier cosine series formula to find the series. Firstly, we need to find the solution of A naught. The formula is 2 on L multiplied by the integration of ft with respect to t from 0 to L. Substitute the L equals 1 and the function ft equals 1 minus t squared into the formula. Solve the integration of 1 minus t squared with respect to t. We get t minus t cubed on 3 with the limit is from t equal to 0 to t equals to 1. The substitution of the upper limit t equals 1 subtract with the substitution of the lower limit t equals to 0 into the resulting integration, we obtain the answer of Fourier coefficient A naught equals 4 on 3. The next step is to find the Fourier coefficient AN, and the formula is as shown here. So we note that when we substitute the function ft 1 minus t squared into the formula, we can see that in order to solve the integration, we need to use an integration by parts method or tabular method. Here, I'm going to use the tabular method to find the solution. In the differentiation column, we have the 1 minus t squared, where we need to differentiate until we get 0. And in the integration column, we have cos n pi t and integrate the cos n pi t 3 times. Cross multiplication of the tabular method, we obtain the solution of the integration is as shown here. with the limit is from t equals to 0 to t equals 1. Substitute the upper limit t equals to 1 into the resulting integration. We obtain minus 2 on n pi squared cos n pi plus 2 on n pi cubed sin n pi. Minus, when we substitute the lower limit t equals to 0, the expression becomes 0. The final answer of the Fourier coefficient an is equal to 4 over n pi squared minus 1 to the power of n plus 1. Lastly, we need to substitute the Fourier coefficient a0 and the Fourier coefficient of an into the formula to obtain the series of the function ft of the even function expansion is equal to 2 on 3 plus the summation of 4 over n pi squared minus 1 to the power of n plus 1, the Fourier coefficient of an, multiplied by the cos n pi t, and the summation is from n equals 1 to infinity. So let's move to the second question of the example, where we need to find the Fourier series using the odd function expansion, which means we're going to use the Fourier sine series to find the series. Firstly, we need to sketch the odd function expansion within the interval t from minus 3 to 3, where the L is 1 and the period t is 2. Here is the plot of the half-range function from 0 to 1, and the expansion into an odd function must be symmetric about the origin. Therefore, this is how the function looks like. Then the next step is we just need to expand the plot within the interval minus 3 to 3 by repeating the plot identically. Since it is an odd function, we're going to use Fourier sine series formula to solve the series. You can see that the Fourier sine series formula, the Fourier coefficients a0 and an equal 0, which means the only Fourier coefficient that have to be calculated is the Fourier coefficient bn. The Fourier coefficient bn can be determined using the formula of 2 on L multiplied by the integration of ft sin n pi t on L with respect to t from 0 to L. Substitute the value of L equals 1 and the function ft equals 1 minus t squared into the formula. We can say that in order to solve the integration, we need to use the integration by parts method or the tabular method. Here is the table of the tabular method. In the differentiation column, we differentiate 1 minus t squared 3 times. The first differentiation is minus 2t, followed by the second differentiation minus 2, and the last differentiation is 0, and we put the plus minus signs in sequence. In the integration column, we integrate sin n pi t 3 times. The first integration, we have minus cos n pi t over n pi, followed by the second integration minus sin n pi t over n pi squared, and the last integration is cos n pi t over n pi cubed. Cross multiplication of the tabular method, we obtain the solution of the integration as shown here. with the limit of the integration is from t equals to 0 to t equals 1. When we substitute the upper limit t equals to 1 into the expression, we obtain these two terms, minus when we substitute the t equals to 0 into the expression, with cos 0 equals to 1, we obtain this expression. Simplify the answer. We get the Fourier coefficient Bn equals 2 over n pi plus 4 over n pi cubed multiplied by minus 1 to the power of n plus 1 plus 1. Lastly, we substitute the Fourier coefficient Bn into the formula and we obtain the solution of the ft equals the summation of the Fourier coefficient Bn, 2 over n pi plus 4 over n pi cubed multiplied by negative 1 to the power of n plus 1 plus 1 multiplied by the sine n pi t, and the summation is from n equals to 1 to infinity. So it's the end of the example 4.13 of the half-range series. In this slide, you are given an exercise question. The function is minus x, where x from 0 to pi. First question is to sketch the even and odd expansion of the function. And the second question is to find the Fourier cosine and the Fourier sine series respectively. The answers are given so that you can check your answers. So here is another exercise question for you. Please try to solve the questions to test your understanding of the half-range series. That's all from me. Thank you.